Okay, at a certain temperature. Everybody happy with that? And the equilibrium law expression is, well, I've just written that. Because they're much, much the same.
Okay. I'm gonna shit over that. Can't get it.
I'm going to make you say it every time.
Le shit in you. What is that? What is that? Is that like an express, like an accent mark over the end?
Oh.
Yeah.
So, Le Chatier's principle. Or I should go ask my son's French immersion school teacher.
That's an unfortunate principle.
How are you supposed to say it? In fact, I should just go ask Jacques, right? Is that we can, the K remains the same always, as we said, because it's a constant, but we can change things to favor the products or favor the reactants momentarily. And the things that change it are pressure, temperature, and I'm missing one. What one am I missing? Concentration. Okay? So we spend a lot of time looking at his principle as well. All right. So let's focus on this for now. The equilibrium law expression. This isn't my handwriting. This is a teacher I worked under a long time ago and when I was training, but they are good notes, so I've kept them for you. Empirical evidence reveals that there's a mathematical relationship between the concentrations of reactants and products at equilibrium. Using the following general equation, this mathematical expression is this. If I have a reaction that goes, these are the balance coefficients, little a, little b, little c, little d. Those are the balancing numbers. Big A is the chemical, big B is the chemical, C is the product chemical, D is a product. Okay? I can write the chemical equilibrium expression, right? The constant for the equilibrium is equal to, square brackets meant concentration. Remember seeing those before? Square brackets for your concentration. Have we used those yet in Chem 20, 30, I mean? No, maybe we haven't in Chem 30. In Chem 20, we used them a lot when we did pH.
Yeah.
Okay, so pH is equal to negative log concentration of H plus. Do you remember that?
Yeah.
Square brackets meant concentration.
Yeah.
So these square brackets as well mean concentration. So the concentration of C, and concentration is measured in moles per liter most often, and certainly here it is. So the concentration of C to the power of the balanced equation times the concentration of D to the power of the coefficient balance. Get where I'm getting these numbers from? And what did we say in our last page? We said that it was the product concentration divided by, so those are products, right? Products. See how that's all the same thing. Just said a little differently, or a little more specifically now. And then the reactants at the bottom, concentration of your chemicals to the power of the coefficients, multiplied together. Everybody okay with that?
Yeah. Yep.
Okay. So, here's a little caveat that you need to make sure you know.
Caveat.
Yeah.
What's that mean?
It means a little note, a little exception. A caveat to the rule is like a...
Is this English class?
Yeah, you guys are getting a lot of vocabulary from me today. Okay, so pure solids and pure liquids are not normally included in the equilibrium expression since their concentrations do not change. What's the concentration of pure water? Right, exactly. What does concentration mean? How many moles of copper sulfate are dissolved in the water? Right, if I have some water, how many circles are copper sulfate? If I have a lot of circles, it has a high concentration. Let's go to something quite normal, like, is it called Mio? The squirt stuff? Mio? Okay, so if I'm squirting Mio in a thing of water, the concentration, if it was really concentrated, I'd have a lot of Mio particles in my water. If it was quite dilute, I'd have just a couple Mio particles in my water. That's what concentration means, right? And mole are those circles. How many moles do I have per liter? Okay, 1 mole per liter or 10 moles per liter. Right. What's the concentration of pure water? How many moles per liter in pure... Oh, no, that doesn't make sense. Right? And the same thing for pure oil or pure ethanol or pure... What's the concentration of copper wire? It doesn't make sense. So if we have a solid in our equilibrium, like we did here, right? NaCl solid, equilibrium arrows, Na plus aqueous and Cl minus aqueous. How many moles per liter of the Na plus ions? That makes sense. Moles per liter of Cl, that makes sense. How many moles per liter of the solid at the bottom? Doesn't make sense. So in my equilibrium expression for this, I would not use my solid because it doesn't make sense. There are times where we do use it. They come later on in the unit, but it's because they're all solid or all liquid. Then we'll use it. Okay, so I don't have sodium chloride as my example typed up here, but rather I have calcium sulfate. But you see how this is the same thing. Okay, so an ionic compound that's only slightly soluble will exist in an equilibrium between the solid, tiny, tiny bit that dissolves, tiny, tiny bit that crystallizes. Or I've just second guessed whether it's highly soluble or slightly soluble. We'd have to look in our data booklets. I think it's highly soluble, actually. Anyway, so the K equilibrium is going to equal my product. Oh, wait, it's a solid, so I don't include it. Divided by the reactants to the power of, oh, they're both to the power of 1. So this is the equilibrium expression for this equilibrium reaction.
So
Happy?
You don't want us using solid to find our concentration?
Sorry?
You don't want us using the solid to find our concentration?
You might have to use the solid to find the concentration. No, they won't later on.
Yeah.
Not now.
Okay.
However, if the reaction contains nothing but pure liquids, then they are included. What is this? You guys just wrote a test on it. What is this? What kind of reaction is that? It's esterification. Okay, esterification exists in an equilibrium where you have not all, we remove a water and we bring those two together. Not all of it is removed. Okay, only, I don't know, let's make up a number. 3% of it becomes an ester in a water. And 97% of it stays as the carboxylic acid and the alcohol. So this exists in an equilibrium. And as much as the water is ripped off, I also put the water on and make those two back again. And then I rip another water off, make it my ester, and the ester then comes back. And this is where the stinky feet kind of come into play, because carboxylic acids are vinegar. They don't have nice, fruity, lovely smells, but this ester does. So if you get a combination of the two things together, it doesn't smell so great. Did you get it? Okay, that was your class, right? That was on because it was Connor. Okay. Right, so the equilibrium expression for this includes all the liquids, all those pure liquids, because they're all liquids. Everybody all right? Okay, so down here, writing equilibrium expressions. Remember, pure liquids and solids should be left out unless they're the only things present, and we're going to try some of these. So, what would you do for the equilibrium expression for number 1? KEQ equals products divided by reactants. What are my products? So square bracket, which means what?
Concentration.
Concentration of capital C, capital O, Cl2, close bracket. Next. Divided by square brackets. Capital C, capital O, carbon monoxide, and Cl2.
So if there was a coefficient on that, we just use it to the power of?
That's right. We'll do that for here. So stepping it up a notch with some coefficients. Now I'm going to write KEQ, the equilibrium constant, equals
SO3.
right? Square bracket, SO3, and square bracket. So the concentration of SO3 squared divided by
SO2 square
the concentration of the SO2 squared times
O2.
concentration of O2. Very good.
Is that all we do? Like,
That's all we do.
okay.
Where's the trick? Where are you going to make a mistake? That whole pure liquid, pure solid thing. Okay, let's do the next one. And the next one. Do you want me to do them with you, or do you want to just go?
Just
Just go.